So that was like August. I think I did the very
Hi, how you doing, Doug?
So the data build on third, this is the I didn't understand.
Yeah.
One more time.
Yeah.
So. So if this is something that you want I know. I love the fact, especially given the season with the fact. I'm not the idea, I'm from Montreal. I don't think so. The other more. Okay. But I'm a hockey. Wow. Okay, so you're wearing the wrong hat. Well, I'm glad you wore that hat set. Right? I'll be right back. I'm just looking over. Look at you. Nice meeting you. And I do.
Yeah, I'm sure.
So, do you think you guys are going to go for the show or not? Yeah. So I think what we're doing. Yeah. Last now. Where are you? We're on the edge.
Thank you. How are you? Maybe. Good. Hey, Linda. Yeah, let Dave know we're gonna make it. Gary? Oh, there it is. Yeah. Yeah. He doesn't live there. Okay. Yeah, traffic meeting.
I hope it's good.
At least the good thing now is
Sorry about that.
it's only BI that can see you now. No one else can see you.
I'm not like splayed all over the dome, am I?
No.
Good.
It's gonna work sort of, halfway. You'll be able to see most of it. You'll be able to hear it. No, it's a modest side. Nice.
No.
Okay.
Yeah, but good.
Yes.
Somebody's sitting in this one, I think.
No. My stuff.
I mean, I could sit over there. Mark recommended it too.
Well, Don recommended this seat tonight. No, it's nice.
I'm sorry I can't see anybody, but I think I heard Karen.
Hi,
Hi, how are you?
how are you?
I'm good. I'm in sunny Florida.
Lucky you. Haven't been here in a while.
Yeah. Yeah.
Next door.
We're talking about next year's. Rhea.
I was just finishing.
Yeah. That was a secret advantage the last time. We said July, and so that wasn't in. Yeah.
I just like Sandy.
Yeah.
Oh, somebody likes- Anyway, members and friends, people who've been here for the first time, a warm welcome. This is a special meeting for the Chesapeake County Astronomical Society. Mark Gagne from the faculty, the responding faculty of Westchester, has graciously agreed to give us an incredible program tonight in the new observatory, which our club has had a little bit to do with, so it's really feels special, especially going out on this weekend. A couple of announcements. First of all, we are proud to announce that we have a new observing chair, Mike Manning, who is not here tonight. I think he found out, but I was going to announce this, he decided somewhere else. Yeah, actually, yes. But he's taking over Don's job on that, and he's ready to go. Anybody that has any ideas or wants to express any desires for any particular observing events that they'd like to see, what they'd like him to do, please feel free to get in touch with him. He's all ears and he's very gung ho to really get us out there. Don Knapp, who wears multiple hats for this club, has also said that he would be very happy to sort of let maybe another club member take over the Night Sky Network job, which is not a very onerous job. It sort of has to do with astronomy clubs sort of out in the United States and how we interdigitate. Anybody that would be interested in doing perhaps an hour's worth on the computer, mostly stuff on the computer, to kind of keep us in that network and appraised and everything, and keep members apprised of what's going on with the Night Sky Network. Feel free to either talk to me or to Don Knapp about that. He would love to help. It's despite the fact that he's not going to be observing chair anymore, he still has plenty to do. So anybody that would be interested in that, let us know. We have a couple of observing events coming up, one of which is tonight, believe it or not. The Westchester Student Astronomy Club is, I think, going to have an event, which is going to be right across the parking lot this way here. Anybody that can help out with that or wants to go, I don't know whether we're going to have any clear skies to be able to see anything, but clouds and skunks. Anybody that can go out and sort of have fun with the kids, please do so. We have on Friday in this week our monthly observing session at BVA, Branding Line Red Clay Alliance. So I just wanted to remind everybody that that's coming up as well. On the 28th of this month, there's an observing session at Wolf Hollow at Glen, Pennsylvania. This is a good event, and we get a lot of people for this. We need scopes, okay? Anybody that can grab a scope or a pair of binoculars with your expertise, whatever it is, we're going to need help with this event. So as many members we can get out there to help share the sky with the public on this one. It's always well attended. The crowd is great. It's always a good conference. So please, whoever can, show up.
Dave, what was the date again?
I have it Friday the 28th.
Thank you.
And of course, next month we'll have our monthly meeting. The 12th of next month will be our monthly observing session at BVA, and Hoops Park right here in Westchester is coming up on Saturday, May 20th. Okay, That's another event that can be very heavily attended. We're gonna need club scopes for that as well. So anyway, we can, keep an eye on the sky and weather forecast. Mike, or Don, or myself will be also watching the weather very carefully and have to let the members know that's together. We're gonna need help with all those things. And with that, I would like to, where's Bruce? There, Bruce, let him take it over and announce our meeting tonight, although glad to see so many faces are here. It's gorgeous night.
So Dave mentioned, we're really very thankful that Mark Gagne from Westchester University agreed to do this event. Just by way of background, you may remember last July when Hubble launched and was positioned, were all these events going on everywhere, including Westchester. And Mark coordinated a really good program to give us first images of Hubble. And we talked.
James Webb. James Webb.
Oh, sorry, no, dating myself. Yeah. So we talked at the time, wouldn't it be a good idea if maybe the middle of this year, we had an update of new images, new discoveries that came from Webb, and that's what Mark is going to talk about tonight. So again, many thanks, Mark, for doing this. Thank you.
So hello, everyone. I'm Mark Gagne. I've been here at the university a long time. It's probably a long, 99. And I teach a variety of astronomy courses here. And tonight, we are going to be looking at some of the more recent results from JWST. As Bruce alluded to, I don't know what you were doing on Christmas morning in 2021, but at 7 a.m. I was watching the launch. This is something that I, and I'm guessing many of you, have been waiting for a long, long time. This is sort of the future of astronomy. I think we're going to be seeing fewer and fewer missions that cost a lot more money, meaning that the science is getting bigger. It's getting harder and harder to fund. And the scientific questions that need to be answered need serious hardware. So I want to talk a little bit about the telescope and the hardware. I want to talk about what it can do, where it is in orbit. And then I want to show you some recent results. I hope I don't get too physicsy with you, but I am going to get a little bit physicsy because part of what we're doing scientifically with JWST really requires us to move in an entirely new part of the electromagnetic spectrum, which is really the infrared. So I'll try to explain why we need to observe in that part of the spectrum and try to give you some perspective on how powerful this observatory is going to be over time. Okay. I recognize you from the other night. All right. So I thought what I would do is I would bring the lights down, do a show for maybe a little under an hour, bring the lights back up, give everybody a chance to really ask questions if you want. I think this is a real opportunity if you have questions either about the science or the technology or the future or future missions, or just some pie in the sky question you've been wondering about. This will be a good chance to have a conversation. And so I encourage you to just ask away actually. Are there any questions before we get started? I'm going to use a microphone. If the microphone is not loud enough, please tell me and I'll try to turn it up. If it's too loud, tell me and I'll turn it down. Sound good?
Yes.
Right, thank you. So I like to start with a little video to get us a little inspired here. I think most of you will recognize the speaker.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth.
So that was, of course, Carl Sagan speaking to us. I want to show you a little video that was actually made just before the launch. And it's, you know, I've been trolling around looking for something better, but it's still really the best explanation of what the telescope is going to do. So I thought we would start by looking at that video, and that'll give us a bit of an introduction about what it took to build JWST and what it's doing for us.
Thumbs up from Jean-Luc Boyer. All systems are go. We're inside a minute now. T-minus 30 seconds and counting. Standing by for terminal count.
À tout de vidéo, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, stop.
And we have engine start. Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported. And let's go down to the floor in the Jupiter Control Center to Raphael Chevrier of Arianespace. Raphael, so far so good.
Hi, Rob. So far, so good. Everything is nominal, as we say, with attitude and trajectory of the Ariane 5 is going perfectly well.
Okay. So let me show you the slightly different video here.
This is the science mission on par with the Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many have spent their entire careers, built the James Webb Space Telescope. It all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1 million miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time, almost 14 billion years to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4 meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our rocket to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To keep the fairing size limit, we built Webb to fold like origami to fit inside the rocket fairing.
And this brings us to our most challenging part of this mission, unfolding it in space.
Got it. Think of what you're doing. You're taking this extraordinarily delicate, precise, state-of-the-art scientific instrument. You're slapping it on a rocket. And for the next 8 minutes, the explosion from that rocket is following you in outer space. Vibrating. Shaking. Everything that goes in outer space has to live through this environment and work once it gets there without having someone come to fix it.
2 weeks. That's how long it would take to fully deploy the Webb telescope. We can take longer if we need to, but those 2 weeks after launch are going to be nail biters. This is the Mission Operations Center at the Space Telescope Science Institute in Baltimore. Those 2 weeks after launch will be like our Super Bowl, World Cup, you pick the analogy. Years of training comes down to these moments.
The Webb Observatory has 50 major deployments, 50 depending on how you categorize them, and 178 release mechanisms must work to deploy those 50 parts. Every single one of them must work. Unfolding Webb is hands down the most complicated spacecraft activity we've ever done. Then again, nothing about Webb is easy. We've never done any of this before. There's nothing simple about sending anything into space. You can't do it without taking risks.
This mission is squarely in new spacecraft territory. Webb is the perfect example of science desire driving engineering capability to new frontiers. Webb's unique design was born from reasoned engineering to accomplish its science goals.
Here's the plan. Shortly after launch, we have a full Webb solar panel for power and a high-gain antenna for communication. About 12 hours later, we have an important engine firing that sends Webb on the proper course towards its orbital destination, about 1 million miles away. That's where Webb will do its science. Webb will be moving so fast, it passes the moon's orbit in 1.5 days. Half the time it took Apollo astronauts to reach lunar orbit. First, we lower the sunshield power. Then raise Webb's primary mirror and instruments away from the sunshield. The solar wind will push us around with the sunshield open, so we'll unfold a drift tack to help keep us stable.
We got these huge, iconic, golden segmented mirrors that will help us deliver amazing new images from the cosmos. But in some ways, the sunshield is a lot more complicated, and it's just as essential. Without it, nothing works.
Here we've got 5 sunshield layers, approximately 8,900 square feet, almost the size of 3 tennis courts, a very thin Kapton material, about 1 to 2 thousandths of an inch thick. Making them go where you want them to go in 0G is extremely challenging.
The sunshield shades the telescope from the heat of the sun, earth, and moon. The concept is simple, but there is nothing simple about the design or operation, especially when you get to space. Webb's sunshield assembly includes 140 release mechanisms, approximately 70 hinge assemblies, 8 deployment motors, bearings, springs, gears, about 400 pulleys, and 90 cables totaling 1,312 feet. All this just to keep the sunshield under control as it unfolds. First, we release these special restraints that protect the sunshield during launch. They roll out of the way, but not all the way until we are ready to deploy a side. Next, we release a set of covers over the core region. Now comes the critical point. All 107 sunshield release mechanisms need to fire on cue. 107. They free the 5 sunshield layers, allowing them to extend as the mid-beams deploy.
We start setting up the optics. First, the secondary mirror is extended and locked into place, and a special radiator behind Webb is extended, which helps further lower the temperature of the science instruments. Finally, we open the primary mirror's wings and lock them in place. With that done, Webb is in its final configuration, but we're not done yet.
After 47 deployments, and accomplishing the hardest spacecraft unfolding NASA has ever done, Webb still won't be ready for science.
While the instruments cool, we'll control motors behind each of Webb's 18 mirror segments, the secondary mirror, and the fine steering mirror located inside the center of the primary mirror. We'll precisely align the mirror segments to form a perfect mirror. Then, Webb will be ready to explore the cosmos.
Okay. Okay, so now for a little bit of that promised physics here. So this is the electromagnetic spectrum, and I want to talk about why the James Webb Space Telescope operates in the infrared part of the spectrum. So as all of you know, the visible part of the spectrum is a tiny sliver of the electromagnetic spectrum. And if it's plotted this way with wavelength increasing this way, you see that a tiny piece of the wavelength space is for these high energy photons, this high energy light, which has shorter wavelength than visible light, but then the electromagnetic spectrum really opens up. There are basically 3 or 4 reasons why Webb operates in infrared. And the one that maybe is the least appreciated has to do with redshift. It is because the prime thing, the 2 prime things that JWST was built to do was to look for exoplanets and to characterize exoplanets. And secondly, really to find the first galaxies. That is to look for galaxies that formed and emitted light at the very birth of the universe. So in order to see those galaxies as they were in the past, we have to find very distant galaxies. And because of Hubble's law, because of the expansion of the universe, that means that those galaxies are also highly redshifted. And so even though those galaxies in their frame of reference, you know, when the light was emitted billions and billions of years ago, most of that light was in the near ultraviolet, and in the visible part of the spectrum, that light is going to be shifted into the infrared. For galaxies, you know, that are rather close by, you know, within a few hundreds of megaparsecs, that's going to be a redshift, which will place it in this part of the infrared. But as we go to galaxies that are 1 billion parsecs away, 3 billion parsecs away or more, that redshift increases and increases and increases to the point that the light that was once in this part of the spectrum is redshifted all the way into the mid-infrared. And so in actual fact, JWST has no cameras to observe the visible part of the spectrum. It starts observing just past, you know, what we would call red, and is actually observing all the way from here, from the mid-infrared, the near-infrared to the mid-infrared. Now, one of the things that we saw in the video a moment ago was the importance of keeping these instruments cool, and that's why those sun shields were deployed. And what I'm showing you here, almost to scale, not quite, is the orbit of the Earth and JWST. It turns out that if you solve the equations of, you know, Newtonian dynamics, there are some special points in the orbit of the Earth around the sun. I'm going to link that forward here. And basically, L2 is one of those points where if a satellite is placed at L2, the Earth and the Moon are always in line. So there's a line between the satellite, the Earth, and the Sun. Now you'll notice that the sun shields are always pointing towards the sun, and the telescope on the backside of the sun shield is always pointing away from the Earth, the Moon, and the Sun. And this is what is actually possible. This is how the telescope and the instruments need to stay cool. I just want to point out that in order to do this kind of infrared astronomy, in the thermal infrared, you have to be looking at something cold. Otherwise, your telescope and your instruments are a huge source of noise. And so, as you'll see in these images, the instruments in the telescope are so cold that there's virtually no noise in any of these infrared images. So why don't we have a look at the first image that was released by JWST last July. And I'm doing this to give you an idea of kind of where we started and kind of where we are today. So this is a fantastic image. This is an image of a SMACS cluster of galaxies. And so you can see the cluster of galaxies all the way up here at the top. And the reason that JWST has looked at so many of these V fields is because of the potential it provides us to see the very, very earliest galaxies. You'll notice these arcs. So remember, this is false color, right? So all of this light is in the near infrared, which means that we're looking at wavelengths of light between about 1 micron and about 5 microns. And so this is false color. Very often what they do is that they'll associate the blue color with the shortest wavelength infrared light, let's say 1 micron, and then they might use 3 microns for the green channel, and then maybe 5 microns for the red channel. And so they create these false colors. You'll notice that there are stars in the line of sight, right? And those you can tell by these beautiful snowflakes. And we'll talk about why there's a snowflake diffraction pattern. And what I want you to keep in mind is that the field of view of this telescope is about the size of my laser pointer here. What I'm telling you is that these 10,000 galaxies are concentrated in a spot on the sky that would be smaller than if I put a postage stamp on the dome. Okay, so it's about less than 2 arc minutes by 2 arc minutes. And this little 2 arc minute section contains about 10,000 galaxies, and those 10,000 galaxies were detected in about a day-long exposure. So the kind of science that we're able to do with JWST is actually staggering, because an image like this was not only not obtainable with the Hubble Space Telescope, but it would have taken years of observing time to obtain. Let me give you a little insight into the instruments that are on the satellite. So the telescope doesn't just have cameras. So it turns out that there are 2 cameras. One is called the near cam, the near infrared camera, which observes between 1 and roughly 10 microns. And then there, 1 and 6 microns, let's say. And then there's a mid-infrared camera, which would observe from about 5 microns all the way to about 50 microns. And if you know anything about the infrared, for example, your body emits infrared light, and that infrared light peaks at about 10 microns. And so what I'm telling you is that by being able to observe all the way to 50 microns, we're able to actually observe fairly cold clouds of gas and dust. There are spectrometers on the satellite that disperse the light to obtain fairly high resolution spectra. There are coronagraphs that are used to block the lights of stars, and this is especially useful for observing exoplanets. I will show you an example in a minute of the microshutter array and what it can do. There are also integral field units that can simultaneously take high-resolution images and low-resolution spectra. And then there are aperture masks that you can use for different observing modes. So to illustrate what some of this does, this is the field that I just showed you a second ago. So this is that first SMACS deep field. So there's the telephone number, SMACS 723. This is the image that I showed you, the near infrared image. And you'll notice that each one of these boxes is basically highlighted by a galaxy here. Now, what we can do with the microshutter array is we can actually put hundreds of spectra, we can obtain hundreds of spectra at fairly high resolution simultaneously. So it can obtain up to 128 spectra at one time. And so when you obtain these spectra, what you see are emission lines of hydrogen and oxygen and other lines of hydrogen, and you see them at increasingly large redshifts. So this is what we were talking about earlier. Normally, these lines would be in the visible part of the spectrum, but when those lines are now seen in these distant galaxies, we see that they're redshifted all the way into the infrared. And these spectrometers on the MSA, on the microshutter array spectroscopy instrument, can actually very accurately measure these redshifts. Now, because the universe is expanding and we know how it's expanding, we can use the redshift to determine the look-back time. So for example, the look-back time for this galaxy based on its redshift is 1.3 billion years. The look-back time for this galaxy based on its redshift is now 12.6 billion years, 13 billion years, and 13.1 billion years. And what that means is that we can use these galaxies seen with JWST really to test our understanding of how galaxies were born and how they evolved over cosmic time, not long after the Big Bang. So if the Big Bang occurs 13.8 billion years ago, approximately, we know that there's this very hot, rapid expansion period, and then the universe cools, the expansion rate slows down. And what we see as the cosmic microwave background is really, as far as we can see, in the electromagnetic spectrum. We know, or we suspect, or computer models tell us that there should be a time which lasts some unknown amount of time, 1 billion years, 100 million years, 500 million years. We don't know how long this period took, but the seeds, the gravitational seeds for galaxy formation took a root at this time here. And then over the course of probably a few 100 million years, the first galaxies and stars formed. Well, already within its first month of operation, JWST discovered the highest redshift galaxy and therefore the oldest look back time that we've ever seen. Now realize, if the look back time is 13.5 billion years, what I'm saying is that if the light takes 13.5 billion years to get to us, that means we're seeing that galaxy as it was just 300 million years after the Big Bang. So one of the main goals for JWST over the next few years is to see how far back in redshift we can go to determine how quickly stars and galaxies formed. And one of the things that we're finding already, just in the first few months of operation, is that this is going back to very, very high redshifts, which means that galaxy formation had to be very efficient. And so now we're sort of re-examining the role of dark matter and the role of black holes in seeding star and galaxy formation early in the universe. One of the images that you might have seen in that early release, I'm showing it here because it's still one of the most beautiful ones for those of you that love planetary nebulae. That this is the Southern Ring Nebula in the near infrared. So you can see this beautiful detail. You know, it's interesting when I talk about stellar evolution and I talk about white dwarf stars and planetary nebula and how stars like the sun are going to die, I always like to point to pictures like this and say, look, there's the white dwarf star. There's the outer atmosphere of the star that's been ejected. And here we are in the planetary nebula phase. And I like to point out that this is what the sun is going to become in about 5.5 to 6 billion years. What's interesting is that so I just want to remind you, this is with the near infrared camera. If we now look at this in the mid infrared, so we look at longer wavelengths, we see a different picture. We see the same shape for the nebula, but you'll notice now that there are 2 stars at the center. And very interestingly, it turns out that the white dwarf is the other one. So I'm sort of revising the way I teach this stuff because it turns out that most of these stars, like most of the stars in the galaxy, are binaries. And that these unusual shapes that we see in planetary nebulae are driven by the binary orbit, and that the mass loss is affected by the binarity. But also what we're seeing in the mid-infrared is the white dwarf star that is emerging from its cocoon of circumstellar material. You know, so that this material that's being blown off is just making the white dwarf visible in the mid-infrared part of the spectrum. So you'll notice those diffraction spikes, especially in the previous image. I just wanted to very briefly kind of talk about why we have diffraction spikes. So it turns out that if we look up here, there's JWST, there are the 18 hexagonal mirrors that make up the primary mirror. Well, it turns out that at the interfaces of the mirror, you're going to have a diffraction pattern. So for example, if you have a telescope like JWST with those support arms for the secondary mirror, it's actually the secondary mirror support structure that is causing those diffraction spikes. In JWST, the hexagonal snowflake actually comes from the hexagonal panels that make up the primary mirror, and then the small diffraction spike is from the support structure, which you see right here on the mirror. And so obviously there were all kinds of simulations prior to launch so that they would understand this diffraction pattern, but that's actually what produces those beautiful snowflakes that we see in JWST images. So these are newer images. You may have seen this on the internet. So this is our good friend Neptune. So what's beautiful with this infrared image, in fact, is that we can see the rings of Neptune beautifully. We can see some of the smaller moons very close to Neptune, but if you turn around and look up here towards the northeast, you'll see Triton. And I want you to be thinking about a little bit of physics here and a little bit about the electromagnetic spectrum. Notice how bright Triton is, right? So Triton is a moon of Neptune, right? It's quite a bit smaller. It's cold. It's made mostly of methane ice on its surface. And that methane ice is very reflective. And it actually looks blue in the infrared. It's basically reflecting sunlight. So even at the orbit of Neptune, 30.1 AU away from the sun, with a giant telescope like JWST, Triton is so bright, look at the diffraction pattern it's producing. My question for the assembled group is, why the hell is Neptune so faint? Can anybody hazard a guess as to what might be going on there? Why is Neptune so faint in infrared light? It turns out that the very upper clouds of Neptune, okay, or the clouds that we see here, are actually in the gas phase. And it turns out that methane is a very, very effective absorber of infrared light. And by the way, I think we know this already, because we know that methane is a very, very dangerous and effective greenhouse gas. So what we're seeing here is actually infrared light that's being absorbed by the methane clouds on Neptune. You'll notice that these methane clouds are reflective, meaning that they're bright. And why is that? Because when you're looking at this part of the atmosphere, you're looking at a higher part of the atmosphere where the storms are. The methane is colder. And in fact, what you're seeing is actually more reflectance from this methane here. So this to me is some interesting physics that you should think about when you're looking at these images. Here's an image I think that was released maybe a few days ago. I don't know if any of you saw this on the internet. This is the first image with JWST of Uranus, our friend, which is a little closer to the sun than Neptune. What is spectacular about this image are the rings. The mid-infrared or the near-infrared are actually perfect places to look for this. You can see how bright the planet is, and it's actually reflecting, more light in the infrared. You can see that all of its moons, Ariel, Titania, Oberon, Umbriel, Miranda, are actually quite bright in the infrared. If we zoom in on this a little bit more, this is what we see. And in fact, you can see that you don't just see one ring, but you see a whole ring system in the infrared here on Uranus. You'll know, for example, that Uranus is actually going through its seasonal change. For those of you that care about Uranus, you know that it's tilted, meaning it was bumped early in its lifetime, so that its rotational axis, its spin axis, is basically in the same orbital plane as its orbit around the sun. And what that means is that the days and the seasons on Uranus are very, very long. And these seasons go through these substantial temperature changes from the sun-facing side versus the side which is facing away from the sun. And Uranus is undergoing one of those seasonal changes right now. Okay. I thought I would go back to Hubble Space Telescope for a moment here. This is a Hubble Space Telescope picture of, I'm sure you know, the Orion Nebula. I had been studying the stars in the center of the Orion Nebula my entire career, going all the way back to the mid-90s, and I actually studied this star, the central star of the Orion Nebula, Theta 1 c, which is a magnetic O-star. So it's a magnetic, very massive star. It's about almost 40 solar masses. It's actually providing about 90% of the ultraviolet photons that illuminate the nebula. And in a minute, I'm going to show you an image taken with JWST JWST cannot observe the trapezium because it is too bright. And so we're going to focus on this bar called the optical bar. I'm sure many of you in this room have either observed it with an eyepiece or you've taken astrophotography of the nebula and you know the optical bar quite well. Now, one of the things that we've been able to do over the years, especially with Gaia, which is the satellite that's obtaining stellar parallaxes to many, many stars in the galaxy now, is that we can actually map out in 3D what the nebula and the stars in the nebula look like. So I wanted to kind of share that little 3D flight through the Orion Nebula with you. So obviously, we're starting with the galactic scale here. There's the Orion Nebula here. And as we get closer, we're going to see the famous Hubble Space Telescope picture of the Orion Nebula zoomed out. This one is going to come over here. We're going to see what was the best infrared picture of the Orion Nebula that we had before JWST, which was taken by the Spitzer Space Telescope about 15 years ago. And based on this imagery, along with the Gaia information, we can actually begin to take a flight through the nebula. So that if you remember the colors, the kind of blue and purple colors are optical light, the green, yellow, and red colors correspond to infrared light. And all of this information now, including computer models of the nebula, allow us to really see deep into the nebula. And so what we see as the optical bar is partly a combination of an overlying neutral lid that is between us and the stars of the trapezium, but also this wall of molecular emission. So I want you to keep that in mind when you look at pictures of the Orion Nebula. One of the reasons that we can see all these stars forming is that the Earth basically is in this direction here, basically towards the top. So we can see down into the nebula, and essentially the radiation and the winds from these massive stars in the center of the cluster have essentially carved out this bubble and ionized the gas. So we have an ionized H2 region here. You can see as we fly by, you can see the proplyds and the protoplanetary disks. So this region contains about 2,000 stars. Those stars are anywhere from about 500,000 years old to about 1 million years old. And one of the things our research is showing us, in fact, from the X-ray spectroscopy and the X-ray imaging that I do, is that we've actually been able to determine that there has been at least one supernova already in the Orion Nebula. And we know this because we can see the hot gas from the expanding supernova. Now, when that occurred, we don't know. It could have happened 10,000 years ago. It could have happened 100,000 years ago or more. But this is basically a fly-through of the Orion Nebula based on this computer modeling. And here we have the trapezium as we fly out from the simulation. And here is that image now taken with JWST of the optical bar in Orion. There's a star which is just visible behind the optical bar, and here are some of the stars here. And so this kind of information, eventually JWST will be obtaining spectra and will be going after some of these fainter stars to look for signs of star formation and planet formation in these very young stars. Speaking of star formation, this is an image that I think came out about a week ago.
Is located 210,000 light years away. It resides within the small Magellanic Cloud, a dwarf galaxy close to our Milky Way. New findings from NASA's James Webb Space Telescope reveal the presence of a much more intricate network of gas and dust structures than previously discovered in the area. Within this plume of gas is cold molecular hydrogen, which provides a perfect environment for young stars to form, some of which can be seen here. These young stars generate energy that heats the gas, energizing and splitting the molecular hydrogen. This effectively area appears to show the head of a dragon spitting out balls of hot gas. Its eye and the balls of gas are areas of active star formation, which will continue to change the environment around it. These wisps are more evidence of that environmental change. Winds from nearby stars are blowing away material that surrounds still forming stars, leaving these small structures behind. Here we see curly ribbons of glowing gas that outline the cold molecular gas of the region. These many pillars of creation show how pervasive the stellar erosion is in the region. Eventually, over millions of years, the mixture of energized and dense hydrogen will give way to thousands of stars and far more of these filamentary structures.
Now, what's interesting about star formation is that very often we're watching stars being born while we also see stars dying. And so one thing that's associated with star formation, obviously, are massive stars. And the most massive of these stars die as Wolf-Rayet stars. And this is a JWST image of a star field that includes a very bright Wolf-Rayet star. But what is amazing that we can see in the infrared, in fact, is all of the mass loss that's been driven off the star over the last maybe 5, 10, 20,000 years. So one of the things that we know from stellar evolution is that these stars, we think, are eventually going to supernova. But what's interesting about this is that it's not clear that they're all going to supernova, because these stars, when they go through this Wolf-Rayet stage and when they go through another stage called the luminous blue variable stage, are losing so much mass, and we see this mass being blown off from the star, that the question is right now in the evolution of massive stars is whether or not these stars lose so much mass that they don't have enough mass to eventually collapse down to form neutron stars or black holes. One of the things I like to point out to my students is we still have never seen a black hole made. We believe that stellar mass black holes are made in core collapse supernovae, but it's not clear that these kinds of stars can actually make black holes. And so this is really an active area of research, and this allows us to see the mass loss. Now, another interesting thing about these massive stars is just like, many stars like the sun are in binary system, many massive stars are in binary systems as well. So this is a computer simulation of what the mass loss would be between these two massive stars. So what we have here is a Wolf-Rayet star. So you can tell that it's puffy, right? Because it's at the end of its life. And around it is orbiting a slightly less massive O-star. And it actually turns out that in these simulations, and you'll notice that the orbits are elliptical. So they're both orbiting the center of mass somewhere around here. And you can see that when the stars are at periastron, that the radiation from the companion star actually blows material off of the Wolf-Rayet star. So that's the model. That was actually what we expected to see. So what does it look like in the data? This, I don't know if you've seen this on the internet yet, but this is spectacular. Let me show you let me talk to you about what we're looking at here. The Wolf-Rayet star is the very bright star at the center here. And what you're looking at is at every periastron passage in this binary, material is blown off of the central star. So the brighter star is here, material is blown off. It takes about 5 years for the stars to orbit each other. That is that every 5 years at periastron passage, another one of these layers is blown out. So this is the layer from the last passage. This is the layer from 5 years before that. This is the layer from 5 years before that, et cetera, et cetera, et cetera, et cetera. Astronomers have been able to find over 20 of these. And what we're learning about here is essentially the mass loss history in the last century of this Wolf-Rayet binary system. And I want you to notice these shapes. Notice how irregular they are. That is the spacing. It looks like the rings in a tree. And what that's telling us is that the expansion velocity everywhere is almost identical, meaning here it's a little bit lower, obviously, here it's a little bit higher, here it's a little bit higher as well. But then the expansion velocities are the same throughout this mass loss history as this stuff expands adiabatically away from the central star. And so for me, as somebody who studies massive binaries and massive stars, this is just a fantastic confirmation of what would be suspected was happening on these systems. And I can come back and show any of these images again after the talk, and we can answer some questions. Speaking of supernovae, this is a Hubble Space Telescope picture of Cassiopeia A. It's not bad. You can see oxygen emission and hydrogen emission around the edge of the supernova. And it looks good. It's fine. This is what it looks like in the X-rays. A little bit more spectacular. Realize that this is X-ray emission, right? So this means that this gas is heated typically to temperatures between about 6 million and 30 million degrees. You can actually see the edge of the shock wave from the supernova. Cassiopeia A is interesting because it's a very prominent supernova remnant. However, we don't know when the supernova happened. And what I mean is that astronomers throughout the world, whether it was in China or Islam or in Egypt or ancient Greece, never observed the supernova. So we don't know what the progenitor of this was. But we think, based on modeling, that the supernova is probably about 1,600 years old. Okay. And what I want to point out here is that if you take spectra, X-ray spectra of a supernova like this, you can actually see the emission lines of iron and oxygen and nitrogen, silicon, neon, sulfur, all of the even Z or even atomic number elements have prominent emission lines in these spectra. And at the very center is actually a source of light, which is actually the neutron star that was formed in the supernova explosion. So that's X-rays. That's not the topic of our talk, but I did want to show you the picture of CCAS that was released last week by the Space Telescope Science Institute. And what we can see now is all of the dust that is formed in these supernova explosions. And so this is a dust that's been heated, that's visible in the infrared and that is cooling. And you can see all of the structure of the supernova in far greater detail than we can see in visible light. Now, what's interesting about this is that the science that we've learned in the last few years, so this is the periodic table, obviously. I told you that this would get really sciencey. Our ideas about where the elements of the periodic table have actually changed substantially just in the last 10 years, partly because of the discovery of gravitational waves. What we've discovered in these gravitational waves events are actually merging neutron stars with merging black holes. Now, obviously, the elements of the periodic table did not come from merging black holes because the black holes just make more black holes. But merging neutron stars lead to explosions that actually create much of the very heavy elements of the periodic table. And in fact, we've actually found evidence for plutonium and neptunium in these supernova explosions. That's new. We thought that it only went up to uranium, but you'll see that all of these heavy elements are actually produced by these merging neutron stars that were first observed by the LIGO Observatory in gravitational waves. It is the first time that we've ever seen merging neutron stars. You'll also notice that, I don't know if, I remember back in the Carl Sagan days, where, we were being told that all of the carbon, nitrogen, oxygen in our body came from exploding massive stars. Well, it actually turns out that most of the carbon and nitrogen on the Earth actually came from dying low mass stars like the sun. That is, at the end of their lives, they go through that asymptotic giant branch stage. So if any of you have observed AGB stars with your telescopes, those stars, when they lose mass, are actually responsible for a lot of the carbon and nitrogen in the universe. Obviously, most of the hydrogen and the helium came from the Big Bang in blue. But you'll notice that a lot of the transition metals, nickel, copper, iron, actually zinc, sorry, that's cobalt, that's copper, that's nickel. They came from exploding white dwarf stars. So these are type 1 supernovae, these are type 2 supernovae, these are merging neutron stars, these are asymptotic giant branch stars. If any of you know, it's really hard to make beryllium and boron. It's actually kind of a mystery where it came from. That was only solved a few years as well, ago as well. So my point is even things as basic as the origin of the periodic table are actually being informed by this brand new science. I want to show you some new pictures of galaxies. Before I do that, I want to show you a picture of a rather famous galaxy called AUC 1365. It is the poster child for a barred spiral galaxy. Like many spiral galaxies, it has a supermassive black hole in its nucleus there. You can see the barred structure. You can see the elongated nucleus of that galaxy. You can see the spiral arms that are being traced out by the gas and dust. This is a Hubble Space Telescope picture. You can see the extended spiral arms down here, where you see lots of blue stars, evidence of star formation. This is typical of an active star-forming galaxy. So this galaxy is actually forming stars a little bit more vigorously than the Milky Way. You can see some of these star-forming regions here, all the way out. I wanted to show you what this thing looks like in the mid-infrared. It looks totally different. So this is the same galaxy. And it just looks weird. And the reason it looks weird, first of all, so that very, very bright source in the middle that was really quite faint in the visible part of the spectrum is actually very bright in the mid-infrared. And that's because of all the gas and dust that are absorbing the light from the accretion disk around the supermassive black hole. So and one of the things that we're seeing from these mid-infrared images, these MIRI is the name of the mid-infrared imaging camera, is that these supermassive black holes are actually very bright in the mid-infrared, which really is telling us that we're seeing right down to the accretion disk. We're seeing right down to that gas and dust before it falls into the event horizon of the black hole. But what we're also seeing is this warm dust in the spiral arms. Every one of these little warm blobs is basically a supercluster of stars that are just being born. And so these, and this is a project called FANGS, P-H-A-N-G-S, FANGS, if you want to look it up on the internet. But if you turn around and you look everywhere here, every one of these red spots represents a supercluster of stars, which are being born in these spiral arms. What's also interesting is you see these cavities in the spiral arms. Those are probably cavities created by supernova explosions that have actually evacuated all of the gas and dust, not all of it, but a lot of the gas and dust in these spiral galaxies. And so this project is looking to really better understand star formation in spiral galaxies. This is still one of my favorite images. This image is probably 6 months old now, so you may have seen this one already. But this again is from the same project, from the same FANGS project. And this is a mid-infrared galaxy, an image of a galaxy called the Phantom Galaxy. So once again, you can see lots and lots of star formation, lots of warm dust. This is not a barred spiral galaxy, so you can see these nice tightly wound arms emanating from the bulge of the galaxy. But what looks different here? This is what looks different. You'll notice that this area in the middle, so you see all of the stars that are formed very close to the central massive black hole. Notice that the massive black hole is actually much, much fainter than it was in the previous image. And that's because it's not feeding right now. And probably the reason it's not feeding is that this whole inner region has been cleared of gas and dust. And so this is really telling us about AGN activity, active galactic nucleus activity around supermassive black holes in these spiral galaxies. We'll also notice these big cavities where some gas and dust have been evacuated. Some of you may recognize this picture. It's about almost 10 years old now. This is the Hubble Extreme Deep Field. And I'm showing you this to give you an idea of what was the state of the art before the launch of JWST. Like I said earlier, there are about 10,000 galaxies in this picture. You'll notice though, and this was actually made over many years with JWST, months and months and months of telescope time were devoted to obtaining this image. If this is a false color image in the sense that the red channel is actually the near infrared channel. The other channels, the red and the green channel, are visible light. You can actually see the noise level in the back of this image projector. In here, it's dark enough that you can see the noise level, and you can see every one of these galaxies. So this is an amazing picture. This is an absolutely stunning picture. Let me show you what came out last couple of weeks ago. This is Pandora's cluster. This is kind of an interesting place. Here's one cluster of galaxies. There's another one. There's another one back here. And there's one up here. This is 4 clusters of galaxies that are actually merging together. The combined gravity from galaxies, gas, X-ray emitting gas, and dark matter creates so much gravity in this image that we actually see tons and tons of evidence of gravitational lensing everywhere here. I don't know if you can see that, but this is gravitational lensing. In fact, all of these little red faint galaxies are only visible because of the amplification that's provided by the gravitational lens. And so the mass of the cluster of galaxies is actually allowing us to see galaxies that otherwise even JWST could not see. And so this has not been fully analyzed. In fact, it's not really been analyzed at all. This is just what the pretty picture looks like. But what astronomers are going to do for years now is take fields like this and obtain spectra of some of the most interesting objects to look really for the oldest galaxies we can see. And I can come back to this picture during the Q&A. Let me share with you a short little
NASA's James Webb Space Telescope presents a new view of Able 2744, also known as Pandora's cluster, displaying various depths of space in a single image, ranging from a foreground star in our own galaxy to the megacluster forming as multiple massive galaxy clusters merge 4 billion light years away, to the even more distant galaxies behind the cluster, whose light is magnified and distorted by the megacluster's warping of space-time. Without the cluster's magnification boost, even the Webb telescope could not see these faint, extremely distant galaxies. Some features that Webb shows distinctly, like this dusty red galaxy, were not detected at all when the Hubble Space Telescope studied the region. Astronomers are using this image to choose certain galaxies for follow-up to get precise distance measurements and details about intriguing features. This small red dot is a distant source of infrared light that has so far defied characterization. It must be extremely compact because even with the visual stretching caused by the cluster's warped spacetime, it still appears as a tiny dot. One theory is that it is a glowing disk of gas surrounding a supermassive black hole in the early universe. Webb's follow-up observations will further reveal the wonders of Pandora's cluster and uncover a new understanding of the universe.
And finally, this was released just a few days ago. Actually, I don't know if you've seen it. So I'm guessing that most of you know what I mean by the North Ecliptic Pole. So if we imagine the orbit of the Earth and all the planets around the Sun, that's the ecliptic plane, right? And so the ecliptic poles are the perpendicular directions above and below the solar system. Now, the reason that this is important is if you remember the orbit of JWST that I showed you around L2, you'll know that the shields, sun shields, are always pointed towards the sun. The telescope is always pointed very often, can always point in some part of the ecliptic coordinate system, but that the ecliptic plane, the ecliptic poles, the north ecliptic pole and the south ecliptic pole are always visible from JWST, which means that JWST, if it wanted to, could stare at the ecliptic pole for a month at a time. And so one of the things that JWST is going to do over the years is stare very, very deeply up here at the north and south ecliptic pole. Now, there's nothing special about this direction on the sky. The only thing about it is it happens to be in the direction of the ecliptic pole. And so it's also giving us kind of an uncensored view of what the cosmos looks like. Now, obviously, I want to point out that the field of view of this entire panorama is about the size of my arrow there. So it's still a very small portion of the sky. Eventually, we think that they're going to count something like 100,000 galaxies in these panoramas. And if you look around, you will see all the little thumbnails here of all the different galaxies that we see here. And this is going to allow astronomers essentially to get a census both in space and in time. Realize that as we look at galaxies at different redshifts, we're also looking back in time. And so what astronomers are going to be able to do with these galaxy surveys is actually be able to unravel the story of galaxy evolution without having to look at thousands of galaxies individually. We're just going to be able to take these deep fields and just expose the heck out of them until we see galaxies at all kinds of redshifts. So this is the kind of science that really is exciting me most coming from JWST, because it's science that we really can't do any other way. The other thing that we haven't talked a lot about tonight is really exoplanets. I will tell you that the exoplanet research program at JWST is really just started. In my opinion, there haven't been any really major discoveries yet, but I expect that as JWST looks at more and more exoplanets, especially in coronagraphic mode, where the light from the star is being blocked, we're going to start to see some very interesting spectroscopy of exoplanet atmospheres. So that's all I have for you tonight. Well, I'm hoping folks have some good questions for me and for everyone else, and let's get started. Yes, sir.
With Hubble, specifically, they're able to zoom in on the galaxies. And do you think with this new telescope, when galaxies are like millions, billions of light years away, they won't be able to look at an exoplanet that's only 5, 6 from the solar system that's only 5, 6 light years away, and be able to actually see the form of the planet with this telescope? Or do you think
So that's just beyond wrong. I mean, even seeing exoplanets, like, you have to realize, right, that the light from an exoplanet is incredibly faint compared to the light from the star. So yes, we'll be able to see individual stars in external galaxies, like Andromeda and other nearby spiral galaxies. We won't be able to see exoplanets outside of the galaxy. In fact, what I'm telling you is that even within 1,000 light years, it's going to be challenging to see the light from exoplanets. And yet, James Webb was designed to do this, but I have to tell you that the actual technology to do this well, actually be able to see the resolved planets, is still a generation back. It is extremely challenging. It is literally going to require an entirely other level of technology. That said, we are going to start to see spectra of exoplanets. One of the techniques that's being used currently that I could have shown you is what we call a difference spectrum, where we take spectrum with the exoplanet emitting light and with the exoplanet sort of the hot side of the exoplanet being shielded by the star. You can actually take a different spectrum and start to see some molecular features in the atmospheres of exoplanets. That's been seen. None of that is very surprising. We're going to see carbon dioxide, we're going to see water, we're going to see methane and other gases in the atmospheres of these gas giants and ice giants around these stars. You have to realize that a lot of the eclipsing systems have these gas giant planets that are orbiting very close to their stars. So they're not very good candidates for life yet. So this is going to be the kind of thing that JWST makes progress on in the years to come. It's also interesting to me that JWST was planned as a mission, as a satellite that would never have a servicing mission, because that L2 orbit that I showed you is 1.5 million kilometers from the Earth. There's no technology currently where we can send astronauts that far. What's interesting is that the next generation space telescope after JWST is also going to be at the L2 point, but they're planning servicing mission. And that's because SpaceX is going to have a launch vehicle that's going to be able to do this. And so what's interesting is that the technology is evolving. And so, you know, things like going to Mars and other things are going to take some time, but we're actually getting there at a pretty surprising clip, actually. I'm very hopeful. Yes, sir.
Mark, do you have any update on how the primary mirror is surviving micrometeorites?
Yeah, so within the first few weeks, there was a micrometeorite. In fact, there was a micrometeorite hit before science operations began. So during deployment, so one of the mirrors has a chip in it now, or a dent, I guess more precisely. Believe it or not, you can we have modeled the diffraction spikes, and you can see the effect of the dent in the diffraction spike. And so far, I think there's been another major hit since then. We're still learning about our own space environment. And so we weren't expecting that many meteorite hits. And when the first one hit within a few weeks after deployment, I have to admit the people at NASA were worried, because the rate that you would infer from that would actually lead to significant telescope damage over time. Now we're almost a year in, and so maybe the pre-launch calculations were more or less correct. And then the other thing you have to keep in mind, since we're talking about launch vehicles to Mars, one of the things that's evolved in our thinking since the Apollo missions is that we've come to realize how damaging the space environment is. And so one of the real concerns about, sending astronauts to Mars is just the amount of radiation and the amount of particle exposure they're going to have. And so there's a lot of concern about that. I suspect that Elon Musk is going to be a little bit less concerned about astronaut safety. Yes, sir.
Especially with regard to building a telescope that would operate beyond the mid-infrared, because of course technology is going to change very dramatically as you get closer to the millimeter or gigahertz range of spectrum. My two-part question, does it make sense to try to build a space telescope that would operate in that region? And at what point would you want to have a cutoff with regard to your upload on frequency? Because at a certain point, you're not going to be able to see those distant galaxies anyway.
Okay, so that's a multi-part question. So the atmosphere absorbs far infrared light out to about 300 microns. Okay, and so there's that whole swath of the spectrum from about 50 micron to 300 micron, which is still a factor of 6, right? In wavelength, that's still a much wider part of the spectrum than the visible part of the spectrum, or even the near ultraviolet or any of that. There have been satellites that have been flown, like IRAS, that have looked in that part of the sky. That was a British-American collaboration from years and years ago. IRAS hasn't operated really since the 80s, since the early 80s. That part of the spectrum is really not that well explored. You have to realize that there's a problem. The resolution of the telescope, as you all know, is basically the wavelength divided by the aperture. Okay, and so as the wavelength gets longer and longer, the resolution of a 10-meter telescope goes down and down and down and down. And so the problem is that if you go out to 100 microns or beyond, even something as big as JWST would give you relatively poor spatial resolution. You wouldn't really be able to see. And so you would really be looking at dust and star formation. So there is astrophysical interest in going to that part of the spectrum, but to really rival what JWST could do at those longer wavelengths, you have to build a giant.
But that's where they build arbitrarily large.
Yeah, but arbitrarily large, we're talking maybe a 30-meter telescope in space, and that starts to get very expensive. I don't know that that's a priority for NASA right now. I really think the priority for NASA is really going to be HABEX, the Habitable Worlds Observatory, which they're taught. So the next, the Roman telescope is going to be built. It's going to be a kind of a different instrument, a different beast than JWST. It really is going to be more of a follow-on to HST, the Hubble Space Telescope, with a much larger field of view. That is probably launching at the end of the 2020s. HABEX will probably be at the end of the 2030s, and that's going to be the observatory that's going to really allow us to get to the exoplanets. And so any kind of observatory project like that is really, you know, a far horizon, just because these projects are getting bigger, more expensive, and the time is literally, and this is why you have to build them for the last 20 years, because it may be 20 years before the next one comes around. So.
And with regard to the second question, at what point do you not even want to look at that part of the spectrum? Because, for example, because of the Doppler shift, right? So you have hydrogen that's going back, you know, at higher D numbers.
Right.
Frequency of, for example, hydrogen is going to be, I don't know, if it's limited microwave. I don't know.
Right. So I agree that, you know, sooner or later you get to a point, but nonetheless, there's other physics that you can do, and this is what radio physics do. When they observe, it's just that window, the atmosphere opens up in the submillimeter. In that boundary between the far infrared and microwaves is where things are tricky in the submillimeter. That's why you have to build them, you know, on top of the Atacama Desert, on top of Mauna Kea, for example, in order to get above enough water vapor to be able to see into the submillimeter. Then once you get down into the millimeter waves, you can do that from the ground, and obviously it's easier to do that than to build giant telescopes. Yes, sir.
I have a question about the orbit itself. Around the L2 point, first of all, what's the radius of the orbit around the L2 point? Second, how often do they have to do course corrections to keep it in that orbit? And then
they don't. And what's interesting here, they don't really have to do very many course corrections at all. There will be some, but you know, if this is the sun, this is the Earth, the orbit of the moon at this scale might be, well, this is not the scale. Way up over there. The L2 point is here, but what's interesting is that the L2 point, if you actually do the calculations, isn't just a point. It's a divot in the gravitational potential. And so what happens is that the satellite actually orbit around that depression. And so it actually orbits this way. And that's what produces that wobbly pattern as the Earth goes around the sun. And so obviously the beauty of this, and what's interesting is that for those of you that know the Lagrange point, right? We've got L2 here. There's also a corresponding point of orbit location here called L1, which is between the sun and the Earth. And why would you put the satellite there? Well, that's where they like to put sun observing satellites. Solar physics satellites, they are constantly looking at the sun and got the optics and the instruments pointed at the sun, and then the high gain antennas pointed back at the Earth. And this is a great orbit because, and so as you may or may not know now, if I go ahead, there's L3 and L4 above and below. So there are other points that can stay in orbit, and that's where we might put a couple of gravitational waves. Eventually, we want to build a gravitational wave observatory on the scale of the solar system. And so those would sort of all orbit together at these points. And then there's a final Lagrange point L5 on the back side of here, on the opposite side of the Earth in that orbit.
so just to follow, so how often do they actually do station keeping?
Well, they don't really need to very much at all. It's completely stable. So I don't know if you know this, but you know, when we work on satellite projects, we really don't want to use thrusters very often. So first of all, that fuel is expendable. It actually puts deposits on the telescope in the instruments. And so we use gyroscopes mostly to turn the telescope. So we use angular momentum to actually smooth the telescope around. Ideally, as the satellites, so the solar panels are so the solar deflection arrays are here. The telescope is generally pointed in this direction. And what we do is we smooth the telescope around. So in ideal circumstances, you don't get many shots to observe something that an object, an arbitrary star or galaxy is only going to be in the field of view at certain times of the year. It's going to be in the field basically twice a year. And so all those observations, this is why our observing cycles are always 1 year. When we submit our proposals to get objects looked at, we get, if it's approved, then they have to slot us in at the right time. And there's really not that much wiggle from side to side. There's some, but not that much. So there's not that much side to side wiggle. We really have to work with slewing the telescope this way with the gyro wheels, and then those damn things fail. We went through 6 or 7 gyro wheels on HST. It's down to 3. And no more servicing missions are planned. And so if another gyro wheel fails on HST, it's going to have to go into 2 gyro mode, which means that it's going to have very little in the sky. I don't know if you remember the Kepler spacecraft that discovered all the exoplanets. When its 3rd gyro failed, it went into 2 gyro mode. They did one big roll of the satellite to put it in the ecliptic plane, and then it spent the next 1.5 years only observing the ecliptic plane before it finally died. So that's going to be one of the real problems with JWST, is to see how long those gyros last. Yeah.
Mark, you gave that really nice example of the Wolf-Rayet star and the data from Webb. All the images really supported the model beautifully, right?
Right.
I know it's been limited time, but have any of the images or data from Webb really disproven certain models that people thought were?
Yeah, well, like I said, the deep galaxy surveys, the fact that bang, we found galaxies at redshifts 12, 13, 14, 15, 16, and that's just in the first look. We haven't taken spectra of every object in those fields. The fact that we're already at 16.1 and we'll probably be at a redshift of 20. I mean, that's not just a little problem. That's like, how the heck do you make an entire galaxy in a couple of 100 million years from a hot soup? Realize that when we're looking at the cosmic microwave background, we're looking at the universe when it is basically just a soup of plasma or gas at about 3,000 Kelvin. Okay, that's about half the temperature of the sun. It's about the surface temperature of Betelgeuse. So the entire universe is just this hot gas. No galaxies, no stars. That stuff has to expand into normal space. And then the gravity has to bring together the little lumps and that we see, the little fluctuations in the cosmic microwave background. Those density enhancements have to lead to the galaxies that are going to form the stars and everything. Doing that in 100 million years, that's, I don't know, so we'll see. So that's actually what I'm waiting for. I'm waiting for a time when we take deeper and deeper and deeper JWST images and we find no more galaxies of higher redshift. And we hit a redshift wall. That's going to be the cosmic dawn. Okay. And so for me, it's going to be to see whether the supercomputer simulations that have dark matter, dark energy, and the expansion of the universe built in can actually produce supermassive black holes, and the black hole may turn out to be key to all this. They may be actually the seeds that are necessary to build those galaxies. Because what we're going to see before we see anything else, I can already tell you, is we're going to see the accretion disks around the supermassive black holes before we see the first star. And so, yeah. Anyway, that's where I think things are going. The question is, how do we make those black holes to begin with, and how did you make them so quickly? Is it possible that they were somehow vestiges of before the Big Bang. They actually might have been primordial. That's a possibility. It's still an out there possibility, but this is what we're going to be able to do with this telescope. We're going to be able to test things at that level of uncertainty. Yes.
This question I'd like to address as professionals. There are many exciting, very big Earth-based telescopes there. Only one lot of that's probably the resolution, especially with is really exciting.
Absolutely.
But seeing that starts to make me wonder, you as a professional astronomer, are you guys excited about getting time on one of these projects? Are you guys thinking more?
It depends what you want to do.
Let's see what NASA does.
It depends what you want to do. So for example, you're going to be able to do amazing science to redshift 2 or whatever perfectly well with these ground-based telescopes. Remember that there are atmospheric windows in the near infrared all the way out to 3.5 microns. There's that M-band window, there's L-band window at 3.5. There's even a little M-band window at like 4.5. You know, from the top of the Atacama Desert in Mauna Kea, you might be able to do that with those telescopes. My point is that there's going to be lots and lots of mid-redshift work that you can do in the near infrared from these giant telescopes. And it's going to be outstanding. What you're not going to be, and that's actually going to be very important, for example, for getting the expansion better. Seeing more galaxies, seeing type 1a supernovae to more galaxies, being able to determine the amount of dark energy and dark matter in these universe models. All of that is going to be doable with galaxy surveys from the ground. A lot of the exoplanet stuff is going to definitely benefit from the adaptive optics from ground-based telescopes. In fact, I kind of think that we're going to learn more from ground-based telescopes in the next 10, 20 years than we might learn from. So, but the one thing that satellites can give you is precision photometry. And that's been very, very difficult to do from the ground just because the atmosphere. Well, not only that, is that it's you know, there's turbulence, there's all kinds of effects, scintillation effects. It's very hard to get the kind of precision that astronomers would like to be able to get to do exoplanet research. So there's a reason that super huge telescopes like the 30-meter telescope, you know, that horizon keeps getting longer and longer because, you know, the question is how many of those do we need? Because there's one plan in India, there is one plan by the Europeans, there's one plan by the Americans. In fact, the Americans one time were talking about building 2 of them, one in Chile and one in Hawaii. I don't know how many will eventually get built. Absolutely. And then there are all kinds of. Yeah, no, I mean, it's all big science. It's expensive. That's it.
Are there any plans to look at some of our own jobs to, Secretary of State with JRFD?
Yes. So the real thing that's going to happen in the next few months, I'm hoping, is that we're finally going to release the Event Horizon Telescope imaging. So you were asking about the millimeter waves, right? So the Event Horizon Telescope is using sub-millimeter telescopes. They were looking at 1.3 millimeters, okay, which we can see through the atmosphere just, okay, at 1.3 millimeters, but we're using telescopes very carefully synchronized throughout the planet in order to get an aperture, essentially the size of the Earth. And so we saw the Event Horizon Telescope image of N87. Now the Event Horizon Telescope image, so there was 2 observing campaigns done. They're analyzing that data now. There's going to be a press release at some point. We're going to see the supermassive black hole at the center of our own galaxy. There is lots and lots of reason to look at our own, at the center of our galaxy, if only to look for the star formation that's going on there. And one of the things that JWST is going to be able to do is also provide an independent estimate of the mass of the supermassive black hole in the middle by looking at the orbits of the planets, the orbits of the stars around the black hole, but that's going to take years of data in order to do that. So those are the kind of science results that we're going to see downstream. Okay, with more observations. Yes, sir.
When you started the talk, you talked about two main purposes for JWST, one being able to view some of the earliest galaxies, and the other being exoplanets. One of the things I wasn't clear on is that given the sensors are primarily infrared, is there anything about exoplanets that is specific to infrared, or is it the other instruments, which is what
it's mostly the fact that a lot of the reason that the atmosphere is bad to us in infrared, right, is because of the absorption of all those molecules. Well, we turn that around, all those molecules in the atmosphere are emitting in the infrared. And so what we want to do is we want to be able to diagnose those atmospheres. So it's a lot easier to diagnose those atmospheres in the infrared. And the third one is star formation. We want to see into the star forming clouds, so those mid-infrared images of galaxies that I'm showing you are the kind of science that they want to do long term. The idea being you use the nearby galaxies to then be proxies for what you see, right? So the best of both worlds. Now, the thing is that things are changing over cosmic time, right? What we would love to be able to do is get a really beautiful picture of a very old, I keep saying old and young and changing them, with a very long look back time, right? With what you'd like to do is get a really, really high resolution picture of old life. That is a very young galaxy, early in the history of the universe, right? So what they're going to do is they're going to keep going back. And the whole idea is that you then connect that back to the computer models, which are predicting what galaxy evolution is going to be doing. And what's interesting is that the observational technology is moving at about the same pace as the computing technology. So our ability to get better and better resolution in these numerical simulations of galaxy collisions, all of that stuff will get better as our ability to see them gets better. So there's going to be a correspondence between the theoretical piece and the observation piece.
So, quick comparison, I remember hearing the Hubble went up because of its orbit and its orientation and the way that various things, including the sun, to get away. It was actually amazing to me how little shutter time.
That's absolutely true.
Is there how much of a percentage of its time that it actually moves?
So
you know that?
I do. So when we're planning observations, Hubble is just painful. You'll spend a year writing a proposal. You might ask 40 orbits, a big proposal will get 100 orbits of HST time. And in those 100 orbits, and every one of the orbits is 96 minutes, by the time you reacquire the object, you look at and realign the instruments and actually you might get a shutter time of for that 96 minutes, and then you reacquire. Now it's true that even Hubble in its orbit has continuing unit zone directly above and below. If you slew the telescope around, that's a relatively small patch. JWST also has a continuous unit zone, but it's south ecliptic poles. JWST, because of its orbit, is going to be much more efficient because the telescope is bigger, because the instruments are more sensitive, because it's operating in the infrared, all of those things. The efficiency of the telescope, I was shocked. Those deep fields are literally 1 hour exposures, 2 hour exposures, 3 hour exposures. and they don't have to take breaks. They just stare, turn off, move, stare. When that deep field picture came out in July and they told me that this was a few days of observations, it's like, it's insane. It's crazy. It's took, 3 months of telescope time with HST, and they did it in a few hours. With JWST, this is the payoff. But I'll tell you what, when you look at the output that you're getting from galaxy surveys, and then taking that big telescope and staring at one exoplanet and having to stare at it so that you can see the whole, this is when the telescope time to, look at one exoplanet starts to get expensive. When you're thinking, I can literally look at 10,000 galaxies in the same observing time as to look at one exoplanet. This is where the trade-offs come. And I'll tell you, as somebody who's on NASA's exoplanet research program, I realized that getting JWST time to look at exoplanets is super challenging compared to what the galaxy surveys would be.
Not a business except we hope to see you all again next month. What decided to go ahead, Bruce, give us a time.
Yeah, the speaker next month is Dr. Candace Hansen. She's one of the directors for the Juno program, the Juno CAM program. So again, we should be getting a lot of information, some really cool images.
She's gonna juice us up.
Yes. We were waiting all night to say.
All right, thank you all for coming. Look forward to seeing you again next